So we know that the dot product of any two vectors, let's say u and v, and let's say these are vectors in R2, so u is u1, u2, and v is v1, v2. And we know this dot product is defined as the sum of products of corresponding components of u and v. So in this case, u1 v1 plus u2 v2. But it's also defined as the magnitude of u times it also can be expressed as the magnitude of u times the magnitude of v times cosine of the angle between them. So let's say this is theta. In this video, we're gonna go through the proof that illustrates how we get this formula here. Okay. So this proof really hinges on it really hinges on two formulations for this, or I should say for this vector here. And this is a vector u minus v, and to convince yourself of that, if that's not clear to you, you can see that. So this is the tip of vector v, this is the tip of vector u minus v, and this is the tip of vector u. So v plus u minus v, v plus u minus v, this should give you u, right? And it does. When you add them tip to tail, v plus u minus v does indeed give you vector u. Likewise, if we had reversed the direction of this vector, so let's say its arrow were this direction instead. If its arrow were this direction, you'd have u plus this would be here would be v minus u, right? U plus v minus u. So you add u, then you add v minus u, you'll get vector v. But let's go back and let's say we were considering vector u minus v. So its tail would be here, and its tip would be here. And this proof relies on two formulations for the square of the magnitude of u minus v. So we're going to formulate the square of the magnitude of u, vector u minus v, in two different ways. So one way we're going to formulate it is, hopefully you remember that the dot, when you dot something with itself, when you take the dot product of something with itself, it's going to be the magnitude of itself squared. So the magnitude of something squared is going to be equal to the dot product of that something with itself, and that something in this case is vector u minus vector v. And this is going to be the same thing as u dot u minus 2v dot u plus v dot v. And of course, when you dot something with itself, that's equal to the magnitude of that something squared. And really, I should be using double bars for everything here, but actually to not confuse you and to save some energy, I'm going to use single bars for everything. Realize that while this looks like an absolute value sign, it refers to vectors, so in this case it's a magnitude. Really, I should be using double bars though to make the distinction perfectly clear. This usually refers to magnitude, but you can also use single bars, and as long as you put the vector signs on top, it's still clear you're referring to vectors. Alright. Okay, so back to this computation. So this is the magnitude of u squared, and let's deal with this term now. This is going to be the magnitude of v squared minus 2 v dot u. That's the same thing as the magnitude of u squared. It's the magnitude of v squared minus 2 u dot v. Now we're going to express this magnitude of u minus v squared in another way. And this way is going to be using the law of cosines. Hopefully you remember the law of cosines. What it applies to any triangle, not just right triangles. So let's say we wanted to find an expression for the magnitude of this side A squared, and these are really, I guess let's say these are not vectors. Let's say these are just numbers. So well, I guess they could be vectors. So I'll go ahead and make them vectors here. So this is A. Let's pretend this is a straight line for a moment. This is A. How do I want to do this? We'll say this is B, and we'll say this is C. Alright, so A plus B equals C here. But the law of cosine tells us the magnitude of A squared is equal to the magnitude of B squared plus the magnitude of C squared minus 2 times the magnitude of B times the magnitude of C times the cosine of this angle opposite side A. So how does that apply here? Well, in this right triangle, or it's not a right triangle, it's a triangle, we have this u minus v is kind of like our side A. Then u and v are kind of like sides B and C. So this magnitude of u minus v squared, that's going to be the magnitude, be equal to the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle between them. Just like the angle between B and C was angle A, the angle between U and V is theta. So looking at the two formulations for the magnitude of U minus V squared, the first, which was obtained just by rewriting this as the dot product of U minus V with itself, and the second, which was obtained using the law of cosines. You see this one, so we have on the, let's write the first one on the left here. Magnitude of u squared plus the magnitude of v squared minus 2 times the I meant 2 to erase 2u dot v equals the second expression here obtained from the law of cosine, so equals the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times cosine theta. So the magnitude of u squared, magnitude of v squared are common to both terms, or both sides of the equation, so we can get rid of this and we'll have negative 2u dot v equals negative 2 times the magnitude of u times the magnitude of v times the cosine of theta. Divide both sides by negative 2 and we get the u dot v equals the magnitude of u times the magnitude of v times cosine theta, and this is basically the result we were looking to obtain. So hopefully that sheds some light into why this statement is true.